Hi and a very good day to everyone. Welcome to the video presentation of Group 1 from HD3. Today, we will be clearing out all of your curiosity for our question, which is assignment number 4 for FAD1008 Chemistry 4. But before that, let's get to know us. Our group consists of 5 members, which is Ian Glenn LRM Florence, Faiz Haji Ismail, which is me, Anissa Zuraimi, Izan Nadia Hussaini, and lastly, Irene Natasha. So what are we going to talk about today? There are 3 main objectives that we are trying to achieve to make sure that all of our audience understand the best about our topic. So the first one is why boat builders attach zinc blocks to the steel hull of ships. The second one, we are going to talk about the electrolysis principle based on the diagram given. And the last one, we are going to do some calculation on the duration of the electrolysis. Why does boat builders attach zinc blocks to the steel hull of their ships? The answer is very simple. There are 2 main reasons why zinc protects the hull of ships. The first one, zinc acts as a sacrificial knot to protect the steel hull of the ship from corrosion. The second one is zinc is a more electropositive metal than steel. Zinc block is attached to the hull because it has a more anodic potential than steel when it is immersed in seawater. So these anodes will supply the cathodic protection current, and zinc will act as a sacrificial anode to protect the boat from corrosion because it is more reactive than steel. This process is generally called as galvanic corrosion, simply means as bimetallic corrosion. It is an electrochemical process whereby one metal corrodes in preference to another metal that it is in contact with through an electrolyte. So the metal with low standard reduction potential has a high standard oxidation potential, which will act as an anode and undergoes corrosion, whereas the metal with high standard reduction potential acts as a cathode and is protected. The reactive of a metal can be referred through the electrochemical series.
Hello and a very good day. My name is Izan Nadia binti Hussaini with the matrix number U2100883. I'm going to continue the presentation from here. Let's take a look at experiment 1 and experiment 2 included in this question. In experiment 1 is a table of ions, the reagents involved, and the observations that can be seen. Firstly, hexacyanophrate 3 ions changes to blue when iron 2 ion is present, but it forms white precipitate when zinc 2 ion is present. Meanwhile, phenolphthalein changes from colorless to pink when hydroxide ion is present. In experiment 2, there are 2 petri dishes, both containing an iron nail each and gel solution. Petri dish B has an extra zinc block in it. The gel solution in the petri dishes is also called ferroxyl indicator solution. First, let's observe petri dish A. In petri dish A, the ends of the iron nail undergo oxidation. The iron atoms release electrons to form iron 2 ions. The hexacyanophrate 3 ions detect the presence of these ions and turn to blue. The electrons released by the iron atoms flow towards the center of the nail. They are received by oxygen in the presence of water to form hydroxide ions. These ions are detected by phenolphthalein, which turns to pink. In petri dish B, the zinc block is preferentially oxidized, as it is more electropositive than iron. Zinc atoms release electrons to form zinc 2 ions. Hexacyanophrate 3 ions detect the ions and form white precipitate. The electrons released by the zinc atoms are received by the oxygen around the iron nails to form hydroxide ions. This causes the phenolphthalein to turn pink.
My name is Irene Natasha, matrix number U2100951. The question is, use the experiment 1 and 2 to explain why boat builders attach zinc block to the steel hull of ships. As we can see from experiment 1 and 2, zinc oxidized before iron as white precipitate and pink colorization is formed when zinc is placed near to iron nail in the solution of gel with potassium hexacyanophrate solution and phenolphthalein. To protect the steel hulls, zinc block is attached to the hull. We can make conclusion that zinc is more reactive than steel when immersed in seawater, which means that zinc gives cathodic protection and acts as a sacrificial anode. The zinc will oxidize before the steel and protect the steel from any corrosions. Why zinc will oxidize before steel? As we can see from the table, zinc has lower standard reduction potential, which is negative 0.76 volt. This also means that zinc has higher standard oxidation potential, which enables the zinc to act as an anode and undergoes oxidation. As for the steel, it has higher standard reduction potential, which is negative 0.44 volt. This will let the steel act as a cathode and is protected from any corrosion. Now, I will explain what will happen to the iron if the reactive metal is absent. Iron metal will oxidize into iron 2 ions, then combine with oxygen and water to become iron 3 ions. Iron 3 ions then combine with the extra hydroxide ions to form iron 3 hydroxide. It then further dehydrates into rust. We call the rust as hydrated iron 3 oxide.
Hello, my name is Ian Glenn Elarum Florence, matrix number U210138, and I will explore the mystery of question 2a, which is explain the electrolysis principle based on the diagram. But before that, let's begin the electrolysis principle. What is electrolysis? Electrolysis is a chemical process that uses electricity to cause a non-spontaneous redox reaction to occur. The electrolysis cell must be made up of two electrodes connected in a battery and immersed in the electrolyte. According to the diagram, experiment 3 is subjected to electrolysis. However, the electrodes are made up of zinc iron which are reactive electrodes. Zinc plate is the anode, meanwhile iron plate is the cathode, and the electrolyte is zinc 2 sulfate. I always remember the abbreviation CAR and auto, which tell us that the first and final letters signify cathode reduction and anode oxidation respectively. Let's have a closer look at the diagram. At the anode, which is the left side of the diagram, the zinc plate undergoes oxidation to form zinc 2 ions and release 2 electrons. Remember this: oil, which means oxidation is losing electrons, and red means reduction is gaining electrons. This gradually causes the plate to corrode, resulting in a thinner layer of zinc plate being observed. At the cathode, the right side of the diagram, zinc 2 ions and hydrogen ions are present. According to the electrochemical series, hydrogen ions are less electropositive than the zinc ions. Thus, it will be selectively discharged and reduced to form hydrogen gas. Hence, effervescence will be observed.
Assalamualaikum warahmatullahi wabarakatuh and a very good day. I, Anissa binti Zuraimi, with matrix number U21022213, will be presenting question 2b. The bottom of a steel hull of a boat has a total area of 10 meters squared. We want to deposit a layer of zinc by 0.1 mm thick. The current intensity I is kept constant and equal to 1 kA. Calculate the duration of electrolysis. Here are the list of data that we were able to obtain from the question given. Okay, for this question, we will be using the Faraday law formulas, which are Q equals to IT and Q equals to NF. In order to use the formula Q equals to IT, since the question asks us to find the T, we must find the value of the Q by using the Q equals to NF formula. Q is the quantity of electric charge, N is the number of mole of electron required to deposit the metal, in this case the zinc metal, and F is the Faraday constant. So the question has given us the area and the thickness of zinc. Therefore, we can find the volume of the zinc, which is 1000 cm3. With the volume, we can find the mass of zinc using formula volume times density, and we will obtain mass of zinc, which is 7140 grams. With that, we can find the number of mole of zinc using the formula mass over molar mass, and we will get the number of mole of zinc equals to 109.1743 mole. So after writing down the equation and balancing it, we can see that 2 moles of electrons are required in order to produce 1 mole of zinc. So we will find the charge using the formula Q equals to NF, where the number of mole electrons equals to 109.1743 times 2, times with F, which is 96,500 coulomb, and we will get Q equals to 2.107 times 10 to the power of 7 coulomb. With that, we can plug in the value of Q and I in order to find T. So T equals to Q over I. We plug in all the values, and T we will get 21,070 seconds. And convert it to hours, we will get T equals to 5.85 hours. That's all from us. Thank you very much for listening and have a good day ahead.